It looks like it's working. So there's a big blue light right in the middle of this. Okay, so RSA is a public key crypto system that uses pretty much exactly the elementary number theory ideas that we've developed so far in this class. The Euler phi function, the notion of the integers modulo n, etc. And it solves problems that go beyond what the Diffie-Hellman key exchange solves. So remember, the problem that the Diffie-Hellman key exchange solved is if I and somebody else want to agree on some completely random shared secret, then we can do it in full view of other people. What RSA does is it lets you solve kind of two problems. You can publish once and for all, publicly, for all to see, a public key, and then people can use that key to send you messages, to encrypt messages to you. So publish a key, and people can use it to encrypt messages. So it does that. And it also solves an incredibly eloquent and symmetric way that's very similar to this. And I don't know any other public key crypto system that does this so eloquently. It also solves the problem of digitally signing a document. In other words, I can write a message, and then I can do some sort of mathematics that give me a little number, and I send the message, and you get it, and then you do something else, and you get a number, and the fact that those two numbers match up make you think it's highly likely I was really the person that sent that message. So it's a digital analog of like your signature. And that's another problem that RSA solves. And we're going to talk about both of these right now. Okay? Any questions? No, because I haven't really said anything. So now let me explain. So I'm going to, just like before, well, for simplicity for today, a message is just going to be an integer. So this will be some positive integer, not too big. And we're not going to worry about a lot of subtle issues that you need to worry about if you're going to really use this sort of thing in practice. So there's a lot of things you have to worry about. Like, for example, if you encrypt the same message twice, you don't want it to get encrypted in the same way. So you have to do things to avoid that happening. Like add some extra randomness to your message so that when you encrypt it twice, you get something different. Because if you always encrypt attack at dawn in the same way, then somebody who's watching and notices that you attack after sending that message could just wait for that same message to get sent again. And they wouldn't need to know that it says attack at dawn. They would sort of work that out. So you have to worry about a huge number of things that you can mess up when you actually use this. I'm going to just focus on the core mathematics related to our course today. So here's what you do. So I want to set up a system so that anyone here can send me an encrypted message. And here's what I do. So what I'll do is I'll choose two primes, P and Q. These are random primes. So somehow, hopefully very randomly, I choose P and Q. They're distinct, so two different primes. Again, you could very stupidly choose these and make your crypto system horrible. We'll talk about that later. So this is step one. Generate two random primes. Step two is generate a random E, and you may as well assume that your E is in the interval from 2 up through Euler phi of P times Q, with the GCD of E and 5p times q equal to 1. Okay? So, question, what is 5p times q if these are two distinct primes?
PQ minus 2.
No. Yes. Oh, I guess, okay, so 5pq is, phi is a multiplicative function, so it's 5p times 5q. And then 5p, for a prime number p, is p minus 1. So this is p minus 1 times q minus 1. So for me, it's really easy to compute 5p times q, because I know p and q. For you, it might be really hard to compute 5p times q. Well, I haven't told you what you need to know. So I'll tell you the public key for the encryption system is, so let me just tell you that. I publish n, which is p times q, and e. That's it. That's my public key, these two numbers. N and e. I don't know if this is getting, it is. I can't move it. Is that about right? Okay. So I'll just say it again. You generate two primes p and q. You generate a random number e that's co-primed to 5pq, and then you publish n, which is the product of your two primes, p times q, and you publish e. So this is your public key. All right. Notice p and q, those individual prime numbers are not the public key. They're not part of the public key. The only thing in the public key is the product p times q. So I'm going to erase that just to emphasize that you don't know p or q, you only know their product. Of course, in theory, if you know n, you have the information. You have enough information to determine p and q. You just factor n. But in practice, factoring n seems to be really, really hard. Maybe it takes, a trillion lifetimes of the universe using the best technology that we have. Okay? That's the idea. So that's the public key. And this is how you set up the encryption system. Now let me explain to you how you send me a message. So your message, let's assume it's encoded as a number modulo n. So send a message. So here's what you do. So let me write it. Send a message, m for message, and we'll view it as an integer modulo n. Okay? There's a whole art to how you take a message, which is like a whole email message or something like that, and you turn it into a sequence of integers modulo m in a reasonably intelligent manner, and then you send that sequence of integers, and then the recipient then gets a sequence of integers and then turns them back into a message. But that's really has nothing to do with number 3. So you want to send a message. Step 1 is you compute m to the power of e modulo n. It's the only possible imaginable thing, really, given the data. You have a number n and a number e. What else are you going to do with them? And it exactly uses stuff we've talked about so far. You write e in binary. You do repeated squarings, always reducing modulo n. Done. That's all you do. That is how you encrypt a message. Okay? So RSA is pretty simple. That's how you encrypt messages. So now the next step is I have to explain to you how I would decrypt this message. So here's what I do. I use algebra. And I also use basically, I guess, what was it? Euler's theorem. So actually, why am I putting 2? Okay, so send a message, here we receive a message. Here's what I do. 1, So over here, when I was making my encryption system, since I know 5pq, I can compute a multiplicative inverse for E modulo 5pq. I chose my E to be co-prime to 5pq. So let me just sort of throw in here, I guess you can't see it, but, and compute, it just fits here, D with E times D congruent to 1 mod 5pq. Okay? So you can compute this easily using the extended Euclidean algorithm. And I think you know about that by now, right? This is like we're literally using every single thing we've done so far, systematically. So I compute this D. So what I've computed is 2 primes P and Q, and a random number E that's co-prime to 5pq, and then while I'm at it, I also compute D, which is the multiplicative inverse of E modulo 5pq. Okay? Any questions? And now I can tell you how I receive, or really, instead of send, maybe I should write encrypt, because that's really the right word to use. And here, instead of receive, I'm going to write decrypt. Okay, so here are the steps to decrypt a message. So this message is m to the e. I'll just call it S for secret. S is m to the e, so that's the thing that gets sent to me. Now here's how I decrypt the message S. I compute S to the power of D modulo n. Done. That's the result. So that's all there is to it. So, why? Why does that work? Notice that S to the D is the same thing as M to the E to the D. But M to the E to the D is M to the E times D. And you might wonder, why does that help at all? I haven't completely explained that yet, but this is congruent to 1 modulo n, modulo p times q. So I'll write modulo n. And so why is that? E times d is 1 modulo the order of the multiplicative group that we're working in. Oh, I'm assuming that the message is co-prime to n. If for some reason you construct a message and it's not co-prime to n, you've just factored n and broken the crypto system. So you better be choosing, you kind of assume that that doesn't happen easily, otherwise you're in deep trouble. So let's assume that the GCD of m and n is 1. GCD of m and n is 1. I guess if you accidentally created a message where the GCD wasn't 1, then you would send it along with, I just cracked your crypto system. You better make a new one. So, so that should be a very low probability that these are not co-prime. Okay, so I want to say more about this because it's, well, okay, so remember when we were talking about the order of an element of a group? In particular, the order of an element of Z mod NZ star. And we took some element x in here, and then we proved this thing called Euler's theorem, which said that x to the power of phi of n is equal to 1. So, why did I write congruent to 1? It doesn't make any sense. It's not. It's just m, not 1. Sorry, stupid. M to the power of ed is congruent to m modulo n because m to the power of ed minus 1 is congruent to 1. And that's because, let's look at this. So e times d is congruent to 1 mod phi of n, right? That's how we chose our d. And that means that phi of n divides e times d minus 1. So if we raise m to the power of e times d minus 1, we're raising m to a power of a multiple of phi of n. So it's like we're raising, so basically this is m to the phi of n times something else. Let's call it a. But already m to the power of phi of n, that's 1, so I'm just rewriting it as m to the phi of n to the a, but that's 1 to the power of a, which is 1. So what you have is that m to the ed minus 1 is congruent to 1, and now if you multiply both sides by m, you get that m to the ed is congruent to m modulo n. So this is exactly Euler's theorem, but where you just multiply both sides by m. Euler's theorem says x to the phi of n is 1, working modulo n. And if you take both sides of this and multiply it by x, you get x to the phi of n plus 1 is x. And this e times d is just like phi of n plus 1, or at least a multiple of that. Does that make sense? So let me just write that this is just a very slight corollary of Euler's theorem. And this is just properties of the Euler phi function being multiplicative, which we proved using the Chinese remainder theorem. And the GCD stuff is, Euclid. So it's like literally a summary of the class so far. It's all kind of put together in RSA. Yes?
If you get 1, how can you get n? If you get 1. You say n equal to 1, and b minus 1.
This is so important that I'm just going to explain it again right in the middle of the board, even more clearly, okay? That's what I'm trying to do. I'm trying to answer your question as clearly as possible. So you're asking what exactly? Just ask it again.
So you have n on top of the equation. Then you get 1.
Wait, what's the top where?
Sd equal to med.
Here.
Yeah.
Okay.
And you equal to m mod n.
Right here.
Yeah.
How do you get this step?
1 on the bottom of the.
Here?
Yeah. Then you get 1 for that equation. Oh yeah.
I got 1. Yep.
Yeah.
I do get 1.
That's good.
Yeah.
That's good.
You're good?
Okay.
Yep. So this is equal to that, but there's this exponent here, which is exactly the same as this exponent here. I just rewrote it. But then I just rewrite the exponent using the law of how exponents work, and you get this. Okay? It's just Euler's theorem. Euler's theorem tells you that raising to the power of d decrypts the message. It undoes raising to the power of e. And the reason that, like the tricks that are going into this that make this hard are that A, it's difficult as far as we know. The assumptions are that it's difficult to factor integers. So factoring seems hard. And the other assumption is that if you know, let's see. Actually, wait, that's not. I was going to say that the discrete log is an assumption here, but that the discrete log is hard to solve. But actually, it's not at all an assumption here. We're not using the difficulty of the discrete log problem as part of this. When I receive this message S, there's no base. I don't have some like base M. I don't know M. So the nice thing about this is that the one thing we're assuming is difficult is factoring. We're not making any assumption about discrete log being hard or easy. It's just a different problem. Although it turns out that very often techniques for attacking factoring similarly happen to work for attacking discrete log. For example, techniques such as build a quantum computer will break both factoring and discrete log. People can build them, which we don't know. All right, so any questions about this? Now, the last theoretical thing that I promised to explain is how do you sign messages? And this is amazingly eloquent and symmetric compared to any other approach to digital signatures that I've seen. Here's how it works with RSA. So I guess this box is begging to be filled with sign a message. So I have some message that I want to give everybody, or I want to make it available to somebody else, and I want to somehow sign it so that if you believe that these two numbers are really my public key, so that's the assumption, then you'll believe that I was the one that signed the message and that nobody else could possibly have been the signator of the message. Okay? So that's, you have to, it's like a logical implication. If you assume that this is my correct public key and that RSA is really hard to crack, then it had to be me that signed the message, or at least my program. Like, it had to be somebody who knows the private key that signed the message. Okay? So amazingly, and very, very nicely, you can solve that problem using RSA. And here's the solution. Here's what you do. So our message is M. Step 1, compute signature, which is M to the power of, okay, what can you possibly do given the data that I've mentioned so far that we haven't done already? D. Raise M to the power of D, the decryption number, Yn. That is something that I can compute. Nobody else can efficiently compute it because nobody else knows D, but I can compute it. So that's how you sign the message. So the signature of the message, it's like something you would append at the bottom. You might have seen people do this before where you'll see like an email, at the bottom it'll have like some block of random looking weird characters, and they're a signature that they like prove that that message was from that person. So the number that they would put is, I call it sig, but I'll just write T here, just to use a single letter. So T, you just let it be M to the power of D. And of course now there's another thing, you have to verify the signature. So what do you do to verify the signature? Verify a signature. Oops. Okay, so step 1 of verifying the signature is I'm going to take T and do something with it. Can you think of anything left that I can possibly do with T? T to the power of E. Yep, that's exactly right. You compute T to the power of E. You can do that because you know the public key. Everybody knows the public key. So when they send the message, they send M, or maybe an encrypted version of M or something, but they send some way you can get M, and then they send you T, and what you do is you compute T to the power of E, and by exactly the same algebra that we did over there, this turns out to be the same as M, mod N. So you compute this and you see, oh wow, that's M. So the thing that you're verifying is that they really, like the method, you'd get M and you'd get T. And given that information, you would do a calculation with T, namely raise it to the power of E, and you end up getting M, and so you say the signature is valid. And that's it. In Bitcoin, one of the key steps is you take a whole package of information and you digitally sign it. And every single transaction is digitally signed that way. The difference, though, is they don't use RSA for doing the signature. They do something similar, but it uses elliptic curves. And it is much more complicated and ugly, but it's faster and more impressive sounding. But the idea is very similar. And it actually, with what you do is you do kind of half of the Diffie-Hellman key exchange, plus some really weird arbitrary thing. And that's how you get the elliptic curve digital signature algorithm. But we'll do that soon. So, sign a message, verify the signature. Okay, how are we doing now? I'm almost out. So, let me just stop for questions for a second, and then we'll do a live demonstration of this at the beginning of class next time. Okay? So, questions? Yes? I can hear you.
E cannot be pure Q.
E cannot be pure Q?
E or Q.
Oh yeah, because, why?
Because the ED, since E is the not trying to define, oh no, Q3 comments.
I think E could be pure Q. The only thing is that E has to be co-primed to P minus 1 and Q minus 1. So like E couldn't be 2, for example.
So E cannot be P minus 1.
That's right. Exactly, yeah. E cannot be, so like if you try E equals 2, then it won't work because P minus 1 is divisible by E. I mean by 2. And so just here's one little hint as to how you could mess up implementing this crypto system. Let's suppose you implement finding P and Q by you compute a random prime P by some method. For example, you just choose a random number and then you keep trying adding to it until you get something that's prime. And then you take Q to be the next prime after P. Okay, so you have two nice random primes, and then you multiply them together and you do all this. But here's the problem. It's ridiculously easy to factor the product of P times the next prime after P. Why? Because P is incredibly close to the square root of the product of those two numbers. So P is very, very close to the square root of P times the next prime after P. So what you would do, if somebody had chosen their P and Q that way, then all you do is you just numerically compute the square root of n and then try integers around there, and you'll very quickly find P and Q that way. But it would be really easy to imagine somebody messing up and implementing this that way, because you're like, oh, I found one prime, I'll just choose the next prime after that. But that would be an incredibly easy to crack thing that might seem really hard, but you just notice this one trick, and then it's easy. Okay, any other questions? Okay, let's just stop 2 minutes early, and then we'll start on Friday with actual numerical example. So somebody should bring their laptop on Friday so that they can be the person in the audience sending and receiving messages. We're literally just going to go through exactly this, but with really big numbers, like we did before.
Yeah. So you said that two of our... sorry.
Okay, let me just...